right, the next talk is Four Paths to AI by Jonathan Connell and Kenneth Livingston, and it looks like John Connell.
All right, you have the mic. Okay, I'm John Connell. I'm from IBM. Yes, we still think about AI. My co-author is Ken Livingston. He's up in the third tier there. He's from Cognitive Science program at Vassar, which is sort of nearby in Poughkeepsie, if you know where that is. And what we're going to talk about today is Four Paths to AI. Okay, a little bit different from the other talks. I'm not here to give you a prescription of what to do or not to do. I'm just going to give you a sort of description of what's out there. All right, that's where we're coming from. That's better? Oh yeah, I can hear my echo now. All right, so what are the four approaches? What are the four paths? Okay, you didn't miss anything by not hearing me before. Okay, this is how do you achieve AI? Okay, and we're kind of boiling down a broad series of approaches, and we think that there's sort of like four things people bet on. You know, why are you going to win with whatever you're doing? And one of them is the silver bullet approach. And this is, hey, everything is pretty good. We're just missing some little grain of salt. Once we get that little special ingredient in there, voila, everything's going to work great. Other people said, no, you guys are really so stuck on your mechanisms and your algorithms and stuff. What you really need to do is kind of figure out what is the important thing that it has to do, right? You know, does it have to emote? Does it have to have conversations? What is that core value? If you get the core value right, then you can fill in the rest of the details. Everything else will work itself out. All right. Then there's the emergence accounts, which is, oh yeah, we don't need any special, you know, we got the conceptualization right, we got all the mechanisms we need, we just need to pump in lots of something, right? Compute power, data, experience in the world, something. And then magically we'll have AI. And then there's emulation. It's like, you know, you got mechanisms and you got values and stuff, but you know what? You could be completely wrong. Maybe we should take things that actually work in the world, like humans and animals, and start copying them at some level of detail. All right? If we just can make a good enough copy, we don't even have to understand it. It will just work like the original thing did. We can understand it later. Okay? So let me give you some examples of this stuff. Okay, silver bullets. So this is what I said, most technology is there, some is missing, but then they all disagree about what actually is missing. Okay? When you take something, if you pursue this kind of methodology, you know, we're looking for the secret ingredient to make the complete recipe, you have to watch out because maybe you picked the wrong hole to fill. All right? So silver bullets are great for killing werewolves, but they don't do anything against vampires. Right? Not like that. So what are some of the silver bullets? Okay, some people say fancy logic. You know, say, hey, first order logic's pretty good, but you know, we need second order or epistemic or auto-epistemic or some variation of that. Once we get the right sort of core engine going, everything else, it's going to be fine. All right, you can use all your vision stuff, you can use your robotics, you can use language parsers, but we need this logic at the core. All right, so that's their silver bullet. Okay, another silver bullet is, embodiment. You know, you're never going to get the thing to understand physical properties like mass and velocity and weight and stuff without a body. All right, so you got to have some kind of body, whether it's real, like a robot, or virtual, as is in these games. But you know, that's essential. All right, you got to have that component to your system. Another silver bullet, quantum physics. Yeah, this is just like, you know, as you say. There's a mystery in quantum physics, there's a mystery in intelligence. You link them up, maybe the same mystery. You know, maybe God lives in those little Heisenberg uncertainty gap. So, you know, you got to have quantum at the bottom, right? You need that, right? Otherwise, you know, the ghost can't come in and haunt the machine properly, and you'll never have a soul in your machine. Another silver bullet, sometimes proposed, inexact reasoning. Says, yeah, logic. That's approximately right, but man, it's way too brittle, right? Anytime it hits the real world, it tends to break. You either haven't modeled something right, or you can't measure it accurately enough. So we really need to be able to handle these shades of gray, right? Even in like medical expert systems, you see this sort of thing. So, you know, fuzzy logic sort of is nice. You can sort of just describe something in what seems like sort of decent English, and then yet have a smooth control surface result from that. So that's kind of nice, you know. And, the fuzzy nature of it accommodates the bad sensors. Right? If you ever work with robots, you know that you're never sure if the wall is really there or 2 inches over. And you can also do some blending of control actions, right? That's one of the big things in robotics is choosing which action to pick. And sometimes you have to trade off a lot of different things. And so having fuzziness there, not just do action A versus do action B, but think about arbitrating it. That falls nicely into sort of an inexact reasoning thing. Another silver bullet, deep language, says, wow, man, so much of humans are tied up with language. If you don't have language, no one's ever going to even think that you've built something that's human. All right? And it's also a great way to learn, right? There's lots of written material there. I mean, our kids learn by basically looking at written materials, or the teachers feed them material that's been written. An old program that did this is Dyer's Boris program, which is kind of, I still think it's one of the best natural language programs. I mean, it's limited in scope, but what it did was pretty cool. And it's got lots of levels of understanding of the text. It's got all kinds of special data structures for various types of understanding, temporal understanding, emotional understanding, sort of a spatial understanding of what's happening and who's in it. And this is the kind of thing it can do, okay? It reads this little paragraph about these two roommates, and it basically, it's just this text. It's not watered down, it's not pre-digested, it's just this text. And then it can answer questions from it. And you look at the answers to this question, what happened to Richard at home? Well, it never said he was at home, but you know that letters typically arrive at people's houses. You can figure that stuff out. He said, he got a letter. And you look at these answers and you say, well, that computer really understood that paragraph, right? You would think that's as good as human, right? So, in some ways, this is very convincing AI. Unfortunately, as I said, for this particular thing, there was a lot of handcrafting. We just figure out a way to make it auto self-craft, handcraft. That would be nice. So anyhow, those are a sampling of some of the secret ingredients or silver bullets out there that people have talked about. Another one, this is another category of approaches, core values. It's like, don't focus on some mechanisms. Figure out what you want it to end up doing, all right? But then, what do you want it to end up doing, right? I mean, is it very important to have an emotional computer that breaks down and cries sometimes when you tell it to do something hard? Maybe not. But then the problem with core values is, you picked the wrong core value, right? Oops. So many things, just by the way it's structured, so many things depend on that core value. For instance, there's this idea of the four humors. It held sway in the medical field for thousands of years, nearly 2,000 years, right? And the way a fever can be cured is by letting out blood. You get excess humor, and it's a hot humor, and you get rid of it, and the fever will go away. But, it kind of didn't work out that way. So core values, some of the core values are situatedness, okay? It matters that the robot have some consequences for its actions. It has to be in the world and actually be able to interact with the world. You just can't have a box that sits there and answers questions sporadically. It really sort of have to have its own desires. Another one is, hierarchy and recursion. It says, you can build sort of neural network stuff that do simple situation action rules, but how does it ever do something more than that, right? How does it build successive abstractions on top of the next abstractions? Right? You really got to get this way of making abstractions into the core of the system, since that seems so very human. Animals, for instance, don't do it very well. Okay, another property about self-awareness. People say, if you remember the bomb from Dark Star, right, he argues with it, your purpose in life is to explode. And finally the bomb decides, yes, it's okay to explode. And that's an important thing, right? That you can't really be human-level AI unless you understand that you are a human-level AI. So we should focus on that. If we get that right, then all the mechanisms we add in the corners will be suitable. Here's a big one, emotion and motivation, all right? The emotion is not something you add as a user interface, right, to make your system more friendly. It's actually some core aspect of the system, right? In as much as inexact reasoning handles the fuzziness of the world, this handles sort of the value structure of the world, right? And, how do you decide what to remember? How do you choose which action to do, right? How do you decide if a place is a good place to be or a person is a nice person to ask a question of? This is very important. And it shows up in some places that you wouldn't necessarily think of as emotion, right? Stuart Wilson had this thing about exploration policies and reinforcement learning, all right? So this is, for the system to learn, all right, it has to sometimes not just try to optimize its goal, it has to kind of like goof around in the environment, figure out how it works. So how do you figure out how much time to spend goofing around? Well, you can do a small fraction of the time all the time, and then mostly just use what you've learned, right? So, I really am hungry, I gotta go get the food, but sometimes, I'll, turn over rocks and see if there's anything underneath them. Another policy is explore a lot in the beginning and then less and less over time, right? This is like children just play a lot and adults really don't play much. Explore until you have some expected optimal performance, If you're not hungry most of the time, then don't bother exploring anymore because you're good enough for your environmental niche.
2 more.
2 minutes, okay. Right, we'll go through this a little bit faster. But anyhow, it goes on, and he's got about 10 policies here, maybe more. But some of the state-based policies are interesting. If your predictions are failing, then explore more. Right? So that's kind of like if you're confused. If you're not learning very much, then you do some more updating. And if you're in a situation where you're learning something, it's probably a good environment for continuing to learn, and you should actually explore more there. It's a benign environment. And then there's sort of a boredom kind of aspect to it. If there's nothing better to do, then start poking around. Right? So, okay, we'll speed up here. Okay, emergence. Everything's already present, just a matter of scaling the system up. But what fodder needs to be provided to this engine? Right? That's where the approach is different. And the problem with this you have to watch out for is early asymptotes, right? A battery will make the frog's leg twitch, so if we put a lightning bolt in there, maybe the frog's leg will get up and dance around or something. But it didn't work. So emergence, axiomatization, right? This is kind of a thing, is you go into logic formalism, but then you say, well, we have to axiomatize time and space and liquids, and right, there's a lot of things you could possibly write down axioms for. Evolution, okay? So basically, you just give it lots of cycles in some environment, right? So that's what you're giving it lots of, and some general purpose rules for searching and improving itself. And animals will happen. Integration. This is another kind of a emergence thing, right? You got to keep throwing lots of different components all together. This is one of these complete system things, like, oh, it can't work unless it has auditory perception. Oh, without olfaction, it'll never go. Oh, yes, it needs dexterous manipulation. Right? So once you have all those things together, maybe everything will work. So that's another kind of emergence. Common sense, this is just, there's lots of facts. Minsky says a couple million. Once you get up to a couple million, it's like, well, Psycho's trying that. And it's just some examples of some of the millions of facts you might have in your head. Reinforcement learning, right? That's another one, where you just need lots and lots of data, right? Or experiment. It's data, not just data, passive data, this is active data, where the robots actually explore. This was a simple Pac-Man type of game, but even to learn this environment took 15,000 steps. And if you're actually doing it with the real world, about 15,000 steps is a long amount of time. But basically, experience is what you're feeding in here. Okay, now I get to the fourth category, emulation, which is everything you know is wrong, just start copying stuff. But what to copy and what level should we copy it at? So you might want to start copying details that didn't really make any difference at all. Like we don't need feathers on our airplanes. Well, maybe they'd be better if we had them. I don't know. We have something like feathers. We have these little streaks and things. Okay, so emulation levels, well, we need to simulate right at the neuron level, right? Forget everything you know above that. Or we need to do neural networks. Yeah, we understand basically how the neurons function. We now understand, we need to understand the networks, and we'll just copy them. A lot of work on this kind of stuff. Some say human development. Okay, well, children develop from knowing basically nothing, or not very much, to being full humans. How does that happen? Maybe we should copy that process. Animals, you know? Animals are pretty cool. Humans evolved from animals. Maybe we can learn something by not human AI, but animal AI, and then it'll be a little step from there to human AI. For instance, you can teach something like rat learning. And this is kind of nice, this recycling stuff. It uses clicker training, which is operant conditioning. Sociality says, okay, you have to actually talk to humans and learn from them, right? And the more that you talk to them, the more human-like you will become. You'll be emulating them, sort of a cultural transfer here. And Kismet's one example of that, which is really designed to interact with humans. Okay, so these are like the last couple slides here. So what good is this classification scheme? All right, yeah, so we broke down the world into like these four sort of mystical thoughts about why AI is going to work. What good does it do? Well, sometimes there's commonalities within the approaches, which are interesting to look at. For the silver bullets, everyone agrees that there's some kind of substrate underneath, right? And there's only something that you have to add to the substrate. So what is that substrate, right? Is it symbolic or set-based or fuzzy or what? So that's something interesting to know. The core values, okay? Well, a lot of that seems to revolve around language and sociology, right? If you look at some commonalities there. So maybe that's the thing that's useful. Emergence, the big thing with emergence is, it's a scaling phenomenon. So is there any way to guess how much data you're going to need? I mean, is it a practical amount of data? That there are ways to estimate it from looking at one problem versus another. And then this asymptote, which is the Achilles heel of the approach, is there any way you can tell if you're going to asymptote by watching how your system is performing? Yeah, it gets better and better and better at first, but is it going to slow down? Is there any way to predict if that's going to happen? And then emulation, right, some common questions there. Well, what's faithful enough? I mean, do you have to get down to ion channels? Do you have to get down to actually chemistry? Do you have to get down to the quantum level? I mean, how far do you have to go to be faithful enough? And again, are there any common principles that show up in this emulation? I mean, autoencoders, those seem to be fairly popular in the neural community. Heavy in learning, right? It's for sure there, but I don't think people really know how to use it. Entropy reduction, a lot of people say that's important. Reinforcement. So anyhow, the 10,000-foot view of why this is important is, one, it helps to diffuse some arguments, right? So when you say, your system sucks, are you actually objecting to the technology or its methodology? Are you saying, your inexact reasoning engine is never going to pan out? Or are you saying is, no, it's not one little piece that's wrong, it's, the whole system is wrong, you need to go in a different direction. So I think of this as the pacifist talking to the hawk. Now, on knee-jerk responses, a gun won't solve any of your problems, why do you want to be so violent? But if you assume the other guy's methodology for a minute and say, okay, if you're going to fight, at least a gun is useful in this situation, right? So take some of the rancor out of the discussions. And then sometimes there are some cross-methodology issues, right? I talked about commonalities within the approaches. A lot of these things seem to need feedback. A lot of them seem to require language at some level. So that's sort of interesting. And then final thoughts. Well, okay. So we have these sort of four broad categories. Is any one of them going to really win? And, of course, we can take the waffle answer here. So, you might have to combine some of them. Maybe a core value and a silver bullet. So a self-motivation, that's the core value. And then language, that's the silver bullet. Or maybe emulation and emergence together. We'll do it. It's a neural network, so that's emulating the brains. And then emergence, we got lots of web data. We'll just feed all that in. Or there could be others. And I have my own personal view. I have a poster if you want to come see it. But that's sort of the idea. So there's these four categories, and maybe we can learn something by looking at the structure of those categories. Okay, thank you.